Thank you very much, Thomas, for this invitation, and I'm really glad to participate in this wonderful workshop. I think really that's as good as it gets. This talk is a premiere because this project has been finished only very, very recently, and it's quite a complex project, one of the most complex actually I have had in the last years. It is a collaboration which spanned time and space, as you can see with these many affiliations we collected. So in principle, this is the PhD thesis topic of Stefan Käser, who started with me in Stuttgart and now finished in Erlangen, basically. And it is also a project which was carry on after a lot of preliminary work which has been done on different kinds of questions on strontium ruthenate. And most of all, I would like to also emphasize the role of Hugo Strand, who was also one of the main authors of this paper. Then, of course, the collaborators in New York, Niels Wenzel, Antoine, and Olivier, who also participated. Our paper appeared on Archive 2 weeks ago, and everything that has been done there was done with the TRIX package. And I would also like to highlight the TPRF package from TRIX, because there is a lot of two-particle stuff that you will see, which was done with this additional package of the TRIX software. So I feel already time pressured, so I will spare you any kind of an introduction and jump right into the topic. We are talking about emergent phenomena in strongly correlated systems, and in this particular case, we are talking about strontium ruthenate. You have seen this phase diagram yesterday already in the talk of Maria Darkhofer. She told you about the magnetism in this interesting singlet magnetism material calcium ruthenate. Today, I will talk about this corner here, which is the superconducting phase of strontium ruthenate discovered by Maeno and co-workers in the mid-90s. So I'm very thankful actually for the talk by Uli Scholweg just before me, because this spares me some time and I can jump this slide almost entirely, because I don't have to tell you that we have here this kind of tetragonal symmetry band structure with 3 former T2G orbitals at a filling of 4 electrons. And you also already have seen the Fermi surfaces as recorded here by ARPAS experiments. So this is the more recent one from the Baumberger group, this amazingly high resolved signal for the Fermi surface. And here there are also other works. This was done in the Damascelli group in 2014, also on the surface of strontium ruthenate. So what about the comparison of ARPAS versus DMFT? So I'm now going to tell you about the preliminary work that led us to the question about the superconductivity. And we start with the single particle quantities, the ARPAS spectra. So what about ARPAS versus DMFT? So this I picked out. There are many works. So Jarne has worked on this, Kim J has worked on this, the group of Pavarini worked on this. There are many people who worked on this actually. I just picked out this one because this was the experiment theory collaboration of the Baumberger group. And the theory part was led by Manuel Zingel. And you have already heard before that here DMFT was done in such a way that the self-energy of DMFT could be calculated without actually including the SOC, the spin-orbit coupling, in the self-consistency. Pretty much what Uli Scholweg also told you, that this additional local operator could be added, renormalized partially in order to reproduce the experimental results very nicely. And the answer to Henry's question, I think, is who asked about the renormalized parameter of the spin-orbit coupling. The answer can be found, Henry, here in this paper. All right, so let us look, however, a little bit closer, because this will be important for us later, into the orbital character of this single particle Fermi surface. So what you can see here are 2 plots of the same Fermi surface, but I color code the orbital character. And in the first plot, I color code the XY, so the 2-dimensional orbital character. So black means pure XY, and down to white means 0 XY. And you can see here that due to the spin-orbit coupling, actually, there is a big mixture. So these Fermi surfaces are by no means pure in their orbital character. They are named, by the way, alpha, beta, and gamma sheets in this convention here. And the same is true also for the other two orbitals. So you can see that there is a lot of mixture going on in the Brillouin zone. And we don't need much more details, but to appreciate this strongly K-dependent orbital mixing. And this strongly K-dependent orbital mixing actually prohibits also to a certain extent to formulate some kind of pseudospin. So differently from the limit which you have in rare Earth systems where you have such strong spin-orbit coupling that you can define a K-independent pseudospin. This is not possible here. So you would have to define a pseudospin for every K point separately. The important point I want to make, however, in relation to the DMFT calculations, and in particular in the self-energy, which doesn't carry spin-orbit effects intrinsically, is that if you look, if you insert this self-energy, which is purely local in the orbital basis, and look, however, at the basis which is given by the bands which form these Fermi surfaces, so the quasi-particle basis, then you have to make this transformation. And these unitary transformations, these rotations of the self-energy on the Fermi surface will give you a self-energy which has a very strong K dependence. So that means that in a certain sense, the locality which you have on the orbital basis is hidden if you look at the K, if you look at the eigenstates of the quasi-particle bands. So here, that is my statements to this. So we go now to the next level of preliminary works, which is the two-particle observables. And here, Hund was the main actor. Namely, while in the single particle spectroscopy, we picked out the self-energy, the single particle vertex, so to say, taken from the auxiliary impurity problem of DMFT. For the two-particle quantities, which is the magnetic response function, you can take the two-particle vertex from the auxiliary impurity model and put it in the beta-psi-beta equation in order to compare to experiment. And actually, the two-particle level, on the two-particle level, you can hide much less. There is much less ambiguity in the correlation effects. Actually, that's also mentioned by Maria yesterday. So here, actually, you start to put your method really to the test by comparing such two-particle response functions. And indeed, it turned out that with this method, the beta-psi-beta equation for the magnetic response, actually the static magnetic response in this case here, the agreement with polarized neutron experiments you can see here was actually very, very good. And also here, just like in the single particle observables, the spin-orbit coupling was not included on the level of the vertex, but only on the level of the single particle propagator in the diagrams that make up the response function. And also that works very nicely here. However, the further analysis of the two-particle observables had also another conclusion, namely bad news for bubbles. What I mean by this is that the vertex corrections in these materials turned out to be crucial. And even if you dress your bubbles with DMFT self-energies, the results are quite unsatisfactory. And this is actually something that we have seen before. And I just want to make a big bracket here. We know this already from other Hund's methods where the same conclusion was drawn about the necessity of including vertex corrections for these observables. So you cannot get away with bubbles in these materials. Look here in the iron pnictides, the difference between a calculation with a bare bubble and what the vertex corrections do. That's dramatic. Okay, but back to strontium ruthenate. DMFT seems to perform well on one and even on two-particle observable levels. The spin-orbit coupling is, of course, important if you look at the observables, but it can be approximated apparently outside the vertices, which is good news. The vertex corrections, however, turn out to be crucial, and RPA-like approaches might be dubious when you talk about strontium ruthenate. So this leaves, of course, once you've done the single particle observables, the magnetic responses, this leaves the question about what can we say with this kind of theory about the superconducting instability. And here I would like to make a short list about the most important experiments for us, because there is a truckload of experiments. I'm not even listing all of them, but the most important for us are NMR night shifts. I'm not going to tell the story about the previous change in the NMR results, which changed from triplet to singlet. So it's likely a singlet. There are other evidences that the order parameter is possibly or likely a two-component order parameter. This is supported by ultrasound and μSR experiments. On the level of the time reversal symmetry, there is actually no experimental agreement between the different experiments. And Curry effect as well as μSR prefer a time reversal symmetry broken state, while Joseph von Tunneling prefers the time reversal symmetry invariant superconducting state. That's why we have to consider later on both of these possibilities, which I will abbreviate with TRSB and TRSI. So there are other more recent experiments also on quasi-particle interference experiments, and they suggest line nodes along the KZ direction. So what line nodes mean is really that you have a one-dimensional set of quasi-particle along the KZ Brillouin zone. And this is actually a puzzle, because if you look into the symmetry analysis of the superconducting state a little bit closer, then there seems to be a contradiction between the occurrence of a two-component order parameter and of the occurrence of line nodes. I will not tell you details about this here, but this is a puzzle. And this is actually something that we can address. So I told you that there is a truckload of experiments, and there is actually so much experimental evidence that allows you a top-down approach. And there are many works which have worked top-down and asked the questions, given all of the experimental evidences that we have, and look at also the possible discrepancies between these experiments, what are the actual symmetries of the superconducting state? What is the gap function that is actually allowed by all of the experimental evidences? And I would like to highlight here a very recent paper by Stephen Kivelson and Ronny Tomale and others who approached this problem exactly this way. We come complementary bottom up. So we come from a DMFT calculation, and we want to treat superconductivity from our perspective. Now, I will not talk about the derivations a lot, but I have to clarify nomenclature, because there is a lot of, there can be a lot of confusion when I talk about gap functions and so on and so on. So superconductivity, I formulate in the Nambu basis. In the Nambu basis, the basis of this Nambu spinor here, I can formulate the generalized Green's function, which has the normal particle and the normal hole propagators on the diagonal and the anomalous superconducting propagators on the off diagonal. This generalized Green's function can be written in the generalized Dyson equation or the Dyson-Gorkov equation to define the generalized self-energy. And the generalized self-energy looks like this. It has on the diagonal, as you have expected, the normal self-energies, and on the off diagonals, you have the anomalous self-energies. And these anomalous self-energies are often referred to as gap functions. So the anomalous propagator F and the anomalous self-energy delta. There is actually a comment I should make here concerning the spin-orbit coupling. So I told you earlier that if you have spin-orbit coupling, you cannot diagonalize the quantities in spin in terms of singlet or triplet. But if you look at this and you take into account spin-orbit coupling on the level of the single particle propagator, which has worked well for the single and two particle observables, then the generalized Green's function and the anomalous propagator in particular cannot be classified as singlet or triplet. But still, the anomalous self-energy can be approximated in a spin diagonal basis. Closing of this bracket comment. So I will talk for the rest of this talk about this anomalous self-energy, aka the gap function. So the way we do it is we turn an Eliashberg theory with the linearized Eliashberg equation into a non-perturbative theory, and by replacing the pairing vertex in this linearized Eliashberg equation into a non-perturbative pairing vertex. So that means that instead of using here RPA-like bubbles in this pairing vertex, we use the DMFT impurity vertex, which allows us to calculate via the Paquet equations the pairing vertex in order to solve this linearized Eliashberg equation for the gap function. So you might know that this can be considered as an eigenvalue problem, where lambda is the eigenvalue and delta is the eigenvector, and the divergence of the superconducting susceptibility is actually marked by the unit when this eigenvector, when this eigenvalue lambda becomes unity. So that is our probe for the superconducting instability. Now, you might already have guessed that working on the two-particle level, we can never reach the temperatures at which superconductivity sets in. The two-particle vertex, we cannot deal with that down to these temperatures. So we cannot make definite statements here. That's a disclaimer right from the start. But we can identify by looking at different kinds of gap functions at higher temperatures, and the lowest that we could reach with our two-particle approach was 290 Kelvin, we could identify gap functions. And this identification of prime candidates allow us subsequently to ask the question, would this candidate that we identify actually be in agreement with the truckload of experiments that we have? And this is basically the philosophy behind our of the next slides. So the prime candidates are two. We identified two, which we identified by means of their strength, of their size of the lambda eigenvalue, and also of the temperature gradient of the lambda eigenvalue. And those two are, on the one hand side, an interorbital gap function, and on the other hand, what we called F-wave gap function. So let me guide you through this busy figure here. Both of these candidates are actually two components. And the two components you can see here in these two lines. So the first line and the second line, those are two components. On the left-hand side and right-hand side, for both of them, I plot the real part and the imaginary part. And as we are in a three-orbital system, these gap functions, of course, have an orbital index. And this orbital index we represent here by this matrix representation of the gap function. And each of these patches then gives you the momentum dependence of these gap functions respectively. So in reality, you can see that this interorbital gap function seems to be a pairing working between the xy orbital and the xz orbital, and it is it's intuitively directly clear why there must be a degenerate gap, which also couples the xy orbital with the yz orbital. There is a 90 degrees rotational symmetry between the xz and the yz orbital in the tetragonal symmetry, which is why we find those two components to be degenerate. The other gap function that we find is actually orbital diagonal. So there are no orbital off-diagonal patches of sizable order. So here we also have, however, a degeneracy due to the fact that this F-wave gap function is either on the xz orbital or on the yz orbital. So in summary, we have two prime candidates, which are both two components. They are even in parity. Curiously, they are odd in the Matsubara frequencies. They are, oh, sorry, I said something wrong. So the interorbital is actually even in parity, while the F-wave, as the name suggests, is odd in parity. However, they switch the symmetry that the interorbital is actually odd in the orbital symmetry, and the F-wave as an orbital diagonal one is even in the orbital index. Both are singlets, but what distinguishes them also is that the interorbital seems to be very local. Look at the K dependence; it's very small, while the F-wave here has several nodes.
Philipp, you have 5 minutes more of talking time.
Yes, this is in the orbital basis. So we need to go now back to the quasi-particle basis in order to see what these kind of gap functions do on the Fermi surface. And that's actually crucial, because you might say this orbital interorbital gap function, it looks basically k independent. So where should the nodes come from that we see in experiments, and so on and so on. Well, the locality on the orbital basis, just as in the single particle Green's function I've told you earlier, is hidden or can be hidden by the strong orbital mixing in k-space. And that's what we do now. The next figures will be a little bit busy, so brace yourselves. I will guide you through them. We will look now at the delta gap function of the interorbital and the F-wave in the quasi-particle band basis. So this here is the interorbital gap function. We have, as I mentioned earlier, however, two possibilities to combine our two components to either a gap function which is invariant in time reversal symmetry or broken in time reversal symmetry. That's those two possible linear combinations. Actually, any kind of complex phase, it doesn't need to be I, but any finite complex phase here renders the gap function to be time reversal symmetry broken. Now, I don't have time to go entirely through this plot. The focus I want to put on these red arrows, because what you can see here in the lower half of the plot is the gap function plotted along the Fermi surface sheets. And here is this alpha prime sheet, the alpha sheet, gamma sheet, and beta sheet, and we plot it as a function of the angle, which is defined here as phi. And what I would like to point out to you is that this interorbital gap function, which is completely k-independent in the orbital basis, has a strong k-dependence if you plot it along the Fermi surface sheets, and it even goes to 0. Or in the alpha sheet, it actually has zeros, while in the beta sheet it has deep minima. So the same we do for the F-wave function, and we see similar things here. So it looks quite differently in the quasi-particle band basis, but also here we have minima. What is maybe more tangible, however, is the spectral function that results from a finite gap function. And if I insert this gap function into my generalized Green's function, I can plot the single particle spectral function in the presence of the gap function. So as I said, this might be more tangible, as if I look at the interorbital spectral function, when I take the TRSB, the time symmetry reversal broken phase, I can see that I have here this is in k-space along the kz line. I have the maxima sitting on the alpha and beta sheet where they cross the diagonals, while the strongest signals in the F-wave I have on the horizontal lines. And now we look at the quasi-particle interference experiments, which has been done, for example, by Seamus Davis, Andrew Mackenzie, and others here. This is the reference. They identify the nodes or deep minima of the potential gap function where the alpha and beta bands cross exactly the diagonals, which would be exactly in line with our interorbital gap function. So in agreement with the Game of Thrones theme of this conference, we end this episode by a massacre and actually kill all of those guys here, which would be in disagreement with the quasi-particle interference experiment. And the only one that survives, is not falsified, is the time reversal symmetry broken gap function that we get by this kind of linear combination of the two order parameters. I will skip the poor man's fluctuation diagnostics. So we asked ourselves which are the most important fluctuations that make the vertex. And we were able to scale contributions in the pairing vertex in order to answer this question. And actually that leads us to saying that Hund's correlations, namely local spin fluctuations, inter and intraorbital, are dominating also, could be dominating also for the superconducting phase. And there is actually a related work to such possibilities also by Philipp Werner in 2015. So I will just now flash to you another, just on one slide, don't get nervous, Thomas, this is my last slide basically, unpublished work, because we actually have the possibility to also compare the fluctuations that we put into our pairing vertex, to compare these fluctuations directly to experiment by means of RIGS experiments carried out by Hakuto Suzuki in the group of Bernhard Keimer. And here, this is a flash of the comparison of experiment on the left-hand side and the DMFT results for which we have estimated the matrix elements by means of combining the spin and orbital response, the dynamic spin and orbital response functions. And this looks actually quite good because this tells us that the stuff that enters the pairing vertex seems to be in agreement with the RIGS experiments. Okay, I've probably insulted many people by not citing them. There are very important related works to ours, namely RPA study of the gap functions, which can be seen here, and there is actually also a GW plus DMFT kind of study by Schilfgarde group, which is closely related to what we do. And if you are interested, because the interorbital gap functions are a very, very interesting topic by themselves, I would like to feature here work which has been done in the group of Philip Bryden, also by Henry Menke, for Bogoliubov Fermi surfaces. But there are too many references to be given in 25 minutes. So I apologize for not citing probably many and leave you with this conclusion slide. And that's it. Thank you, Thomas, for tolerating this additional time.